Good morning. Today I would like to explain the analysis of common base amplifier. In previous classes we have seen the analysis of CE amplifier and common collector amplifier using small signal model of transistor. Now today we would like to see the analysis of common base amplifier. Okay, so let us see the diagram of common base amplifier using BJT transistor. So this is the common base amplifier circuit using BJT transistor. See here, the base of the transistor is at ground potential and it is common for input and output. In CB configuration, the input is at the emitter of the transistor and output is from the collector. Here the DC sources VEE and VCC provides the proper biasing. Proper biasing means places the transistor in active region. Amplification is obtained if the transistor is operating in the active region, right? And CC1 and CC2 are the coupling capacitors at input and output. The purpose of coupling capacitor is to block the DC and to allow AC signal to the input of the transistor, right? This is simply about the description of the CB amplifier. Now coming to analysis. Analysis, as you know, finding the input impedance, output impedance and voltage gain. Of course, sometimes current gain also. For that, you need to represent the given amplifier in the small signal model, right? Now I am replacing the transistor in the small signal model and all the DC sources with zero value, that is they are maintained as short circuit. Now I am replacing the transistor with equivalent model. What is the equivalent circuit for the transistor? The equivalent circuit which I am using here is hybrid pi model. Okay, in hybrid pi model, from base to emitter, R pi resistor is used, R pi resistor, and from collector we have the current source with the value GM V pi, and from emitter no element, okay. So as for this circuit, the base is at ground potential, so the base, if you observe, it is at ground, input is at emitter, output from the collector. Okay, DC sources are shorted, hence at the input there is RE resistor and at output there is RC resistor. In addition to this, at the input there is a VS source with the internal resistance RS and a load resistor is connected at output terminals between collector and ground. Okay, is it clear? The equivalent circuit, small signal equivalent circuit of common base amplifier. Now the analysis is that is deriving the voltage gain. For deriving the voltage gain, let us take the output impedance of this, output voltage. Let us see the equation for output voltage. So here the output voltage is the drop across parallel combination of RC and RL, and in this combination the flow of current is GM V pi in opposite direction, right? The current is GM V pi into the parallel connection of RC and RL gives the drop of output voltage. Okay, therefore you can write the equation for the output voltage is V naught equal to minus GM V pi into RC parallel RL. Okay, this is the current and this is the resistive network RC parallel RL. Okay, current since Y it is negative means the current direction is from bottom to top, that's why. Where V pi is obtained from the input circuit, let us write the KCL equation at the emitter node. The KCL equation at the emitter node. What is the KCL at the emitter node? Okay, that is Kirchhoff's current law. Kirchhoff the current law is incoming currents is equal to outgoing currents at the given node. Here all the currents are almost incoming, that's why the equation is like this. One current is gm v pi plus another current is v pi by r pi plus another one is v pi by re plus, and the current in RS is the voltage differences between Vs and V pi divided by Rs value, that is Vs minus V pi, Vs minus of minus V pi divided by Rs, that equal to 0. Okay, this is the KCL equation at the emitter node. Now since Gm R pi equal to beta, right? Gm into R pi is beta, therefore the Gm is replaced by beta divided by R pi in the above equation. In the above equation, the Gm is replaced with beta divided by R pi. Okay, so here beta R pi by beta V pi by R pi plus V pi by R pi, both two terms are there with V pi by R pi. Okay, therefore if you take V pi as common, it becomes 1 plus beta divided by R pi, like that. Okay, so therefore finally if you take V pi as common, then the modified equation is like this: 1 plus beta times 1 plus beta divided by R pi plus 1 by Re plus 1 by Rs equal to in the last term we have Vs by Rs, right? If I send that term to the right hand side, it becomes minus Vs by R pi, Rs, minus Vs divided by Rs. Okay, with this the V pi is given as the V pi, therefore V pi equal to minus Vs divided by Rs, and the resistive term from the right hand side I am shifting to the left, from the left hand side I am shifting to the right hand side, so that it becomes like the parallel connection of Rs, Re and R pi divided by 1 plus beta. So this is the V pi. Now substitute this V pi in the V0 equation, so that the voltage gain AV equal to V0 by Vs equal to Gm Rc parallel RL divided by Rs into this resistive parallel connection, that is parallel connection of Rs parallel Re and R pi divided by 1 plus beta. Like that you can derive the voltage equation in the common base amplifier. Suppose if Rs is equal to 0, the voltage gain is approximately equal to Gm into just Rc parallel RL. Okay, Gm into Rc parallel RL. Okay, clear? This is the voltage gain in the common base amplifier. Now let us see the current gain in the same common base amplifier. For a current gain, you know the definition is output current divided by input current. As per the circuit, the output current is I0 and input current is IA. Now writing the KCL equation at the emitter node, okay, see the diagram and write the KCL equation. II plus V pi by R pi plus Gm V pi plus V pi by Re equal to 0. Okay, this is the KCL equation at emitter node. Therefore from this the V pi you can derive it as minus II. The rest of the equation is already previously actually we derived previously also we derived the equation, but there the Ia instead of Ia we mentioned it as Vs minus V pi divided by Rs like that. But now instead of that I represented the current in the form of Ia. Why? Because we have to derive the current gain I naught by Ia. That's why. Okay. So finally V pi equal to minus Ia into the resistance parallel network, that is R pi divided by 1 plus beta parallel to Re. Okay. Now the load current is given by, from the circuit if you observe the load current I naught, the I naught is given by, since the output circuit is a parallelly connected to resistors RC and RL, and I naught is the current flows through RL. Okay, therefore in the voltage in the circuit shunt connection, the I naught equation is directly minus Gm V pi, this is the source current, minus Gm V pi into RC divided by RC plus RL. Okay, now substitute the above V pi value in this I naught equation, so that the current gain AI equal to I naught divided by II, that equal to Gm into RC divided by RC plus RL into R pi divided by 1 plus beta parallel to R. Okay, this is the current gain you can get. Okay, see here, circuit also represented here. See, this is the output circuit. Here the source current is Gm V pi. Therefore the current in the RL is given by the direct equation is like this: supply current minus Gm V pi into other resistance value divided by total resistance value gives the current in RL. Okay, now substituting above V pi in this, therefore the current gain is like this. This is the equation for the current gain in CB configuration. Okay. After that input impedance. Now okay, in the same equation, let us take the limitations with reference to Re and RL. Suppose if here generally Re is infinity, if Re is approached to the infinity and RL approached to the 0, then it is almost equal to alpha value. In CB configuration, you know, the current gain is alpha, or current amplification factor is alpha. Okay, so AI equal to Gm R pi divided by 1 plus beta, but the product of Gm and R pi is equal to beta, right? So beta divided by 1 plus beta, that is equal to the alpha, right? Now coming to input impedance. For deriving the input impedance, let us consider the equivalent circuit is like this. At the emitter terminal, now we are estimating the resistance value. So therefore the resistance looking at the emitter is Rie equal to V pi by Ii, V pi divided by Ii, and by using the Kcl equation at the input, that is Ia equal to Ib plus Gm V pi, where Ib is V pi by R pi plus Gm into V pi. Therefore if you take V pi as common, 1 plus beta divided by R pi. Okay, therefore hence the Rie is, substitute this equation in Rie, V pi cancel, therefore the resistance is R pi divided by 1 plus beta, that is the input impedance in the CE configuration, CB configuration. Now coming to output resistance. For output resistance, there is a condition is the source Vs must be 0, and connect a test voltage at the output terminals, say Vx. And now if you observe, this is the equivalent circuit with that assumption. The assumption is Vs is equal to 0 and connect a test voltage Vx at the output. And now the output impedance is say Vx by Ix, like that you can say. Again write the Kcl equation at the emitter. Kcl equation at the emitter in the above, from the above circuit, the Kcl equation at the emitter is Gm V pi plus V pi by R pi plus V pi by Re plus V pi by Rs. Already previously also we written, okay, that equal to 0. This equation represents V pi equal to 0. V pi equal to 0. That means Gm V pi equal to 0. Therefore, the output when the Gm V pi is equal to 0, that is current source value is 0, means it acts as a open circuit. It acts as a open circuit. Therefore, the output impedance is just RC. The output impedance R0 is just RC. Okay. See here, the output impedance, we are looking at the collector. We are looking at the collector. That's why neglecting RL. Okay. Therefore, it is equal to RC only. It is equal to RC only. Okay. So that is the analysis of common base amplifier. Common base amplifier using hybrid pi model. Okay. Thank you.